Okay, everybody, I'm going to go over simple harmonic motion number 1 here for you, and hopefully you will find that this is not too terrible of an assignment. All right, so let's begin with number 1. As you can see, there's a piston oscillating. You're given the position function, which is always good. All right, so you're going to just plug and chug right here. That's pretty straightforward. Velocity, remember you have to take the derivative of this with respect to time, and then after that, plug and chug. You're going to take the second derivative here, plug and chug, and then once you find the period, and the amplitude, that's going to be a pretty straightforward one as well. Let's see. Oh, well, the amplitude is easy enough. You just read it right off of your equation. Period, you're going to use your period formula because it is a spring. Not too tough. Okay. Simple harmonic oscillator. I sincerely hope this one doesn't take you all that much to do. All right, let's face it, you're given the time here, and if they tell you how many vibrations, remember period is for a single cycle. You want to know, oops, I can't spell while I'm trying to talk. All right, remember a period is the number of seconds per cycle, and then frequency is the inverse of that. Angular frequency, remember we've got that, right? And it's for a spring. We're going to assume that we are dealing with a spring. And so, yeah, this is going to be, in this case, well, actually, no, let's not assume it's a spring because it just say it's a simple harmonic oscillator, but you can just use that relationship. That's a pretty easy one. That's just modified from the period equals 2 pi on omega. And you can just move things about. So there's your first page. Very quick. All right, let's move some things down. Now we're going to deal with the glider. Glider attached to a spring. Force constant is given to you. Get a frictionless air track, and you're given an amplitude. That helps. All right, so you're going to use, pretty straightforward, use the formula here to find the period. You should have everything that you need. When you look for maximum values for speed and acceleration, remember you're going back to those original ideas about, like for example, not a prime, just a position function, right? That is going to be a cosine omega t. All right, just remember, of course, that our maximum values are when we have this going to 1. So we won't use that any longer. And of course, if we're doing acceleration, we'd be using the second derivative. But again, remembering that our maximum is when the cosine function goes to 1. And then for part C, you've got, you take your derivatives and you plug and chug. That's pretty much what they're looking for there. Okay? Number 4, 170 gram block attached to horizontal spring. They tell you the period, you're given total energy. Now this is the one, let's make sure I can, all right, we're talking about really mechanical energy here. And this one I forgot to give you during the notes, but when we did that practice problem, I went over it. For total mechanical energy of a spring system, you want to use 1/2 Ka squared. Okay, so if you're given that total value here, you can just use that. Use that to find K, and yeah, go back and figure out A. Let's see, we've got a period. Actually, if you just do the whole period formula, you should be able to figure out part A, and then you can use this one to find part B, now that I look at that. Okay, block spring system. Let's look at this last one here. 0 centimeters. All right. Spring constant is 250 newtons per meter. Mass of block. All right, determine the mechanical energy of the system. Well, I think I just gave away the big secret there. Right, 1/2 Ka squared. That should do it. And let's see, maximum speed of the block. That's when all of your energy becomes kinetic. So you just set your answer for A equal to the kinetic energy formula. Determine the maximum acceleration. Well, I think you could probably go about that a couple of different ways, I suppose. No, it doesn't say it's a vertical spring. Okay, never mind. If you're working with that second function, or that second derivative of your position function, and you're going for maximum acceleration, that should work pretty well for you there. So you should be able to do that. Or you could say that the maximum acceleration is equal to the spring force and work with it that way. In fact, I think that's probably what I ended up doing, saying that my net force is equal to my spring force. And I would be able to find my maximum acceleration that way. So you get a couple possibilities. Not too bad. All right, last one here, number 6. Okay, so you've got a horizontal spring, no friction, you're given force, you're given an initial position. All right, so you've got your amplitude, you've got your initial force, you've got your mass. Find the force constant on the spring. I should think you should be able to use Hooke's law for that one to figure out your force constant on the spring. That shouldn't be so tough to do. Find the frequency of oscillations. Remember, frequency is the inverse of period. So if you use your period formula, you should be able to just take an inverse for that and find it without too much trouble. Let's see what else we got here. Oh, you know what? Yeah, for part A, did I say Hooke's law? I hope I did. I'm just thinking back on that. All right, maximum speed of the object. Well, let's see. We got a couple possibilities here. You could find the total energy and then find the maximum speed, which would be, you know, when you're at the equilibrium point, everything is kinetic energy at that point. Or you could probably get away with using your acceleration function. You know, the negative omega squared a cosine omega t. You should be able to find, oh, wait a minute, we don't know t. Never mind, skip that one. That wouldn't work. Where would that maximum speed occur? At equilibrium. So you figure out how far off that is off of the, you know, off in terms of x. Find your maximum acceleration. Again, wait a minute, is this the same question from before? Did I print it twice? No, it's not, but it's asking the same sort of thing. I would suggest, again, using Hooke's law equal to ma. I think that would work. Or you could use your acceleration function, noting that the cosine piece is going to go to 1. That should work. Maximum acceleration should occur at maximum stretch. Hopefully we know that. Total energy of the oscillating system, 1/2 Ka squared for that. Find the speed of the object when the position is equal to 1/3 of the maximum value. Okay, so yeah, let's cut things into thirds, right, and figure what do we have at that point in terms of energy, or total energy, and solve. You could do that. That's not so bad, right? You'd have stretch, you'd have some velocity in there. Set it equal. Should figure that one out. All right, and the same thing goes for part G. Find the acceleration of the object when the position is equal to 1/3 of the maximum value. All right, so again, using Hooke's law equal to the net force should help with that. Okay, wandered around a little bit there. I had a couple of extra papers to try to take a look at, but hopefully that will be enough to guide you through the majority of it, and you are, of course, welcome to find me with questions. Have a good one.